we're going to look at the electrophilic addition of something to a conjugated pi system. So you could do Markovnikov additions with something like a hydrogen halide, or you could do it with dilute sulfuric acid and water, or you could even be trying to do something like a free radical halogenation. We're going to look at the addition of a hydrogen halide. It would be important that there was not peroxides if you want to be doing this type of a reaction. So the first thing to do is think about the formation of the carbocation, because you are going to protonate one of the pi bonds. Now you're only going to make one carbocation, so it's important that you form the most stable carbocation. That means you want to be adding to one of the two ends that I've put little green dots on. Don't ever even think about putting the hydrogen somewhere in the middle of the conjugated pi system, because I guarantee it won't be the strongest or the longest conjugated pi system. If you put it here, you'd have a positive charge here and here that would be resonating. So it would be resonating between a tertiary and a secondary position. If you were to put the proton here, you would have resonance between a secondary and a primary carbon. And it would be better to have resonance between a tertiary and a secondary, because those are more stable positions. So when this reaction actually does occur, we're going to use this pair of electrons from the double bond to pick up the proton and give electrons back to the bromine. And the carbocation that is produced will have resonance delocalization of that positive charge through the conjugated pi system. So you want to be looking at the carbons that are sp2 hybridized in this case. And you have a leftover bromide. Now this bromide can add to either of the two resonance structures. It really doesn't matter which one, because this is one carbocation. Now the one on the left, the one where the positive charge is on the tertiary carbon, is the predominant resonance structure because it is on the tertiary position. And if it adds here, you're going to make one product. And if it adds here, you will make a different product. So the two products that you will form without thinking about stereochemistry be this one and this one. Now both of these are going to be formed. But if you're worried about which one's major and which one's minor, which is something you should be thinking about, you need to think about thermodynamic and kinetic control. Thermodynamic control will occur when the solution is hot. So if you heat the reaction up a lot, you're going to favor the more stable product. And as you look at these two products, the more stable one is the one that has a more substituted double bond. So that one would be the one here on the right. This would be the thermodynamic product. This will be the favored product when it is hot. The one on the left is the kinetic product. It is formed from the more stable resonance structure for the carbocation. And so under cold conditions, this is the predominant product. This is called the kinetic product. So if you're hot, you favor the one on the right, the thermodynamic product. And if the conditions are cold, you would favor the kinetic product, or the one on the left. We are going to look at the free radical addition of a halogen to a conjugated pi system. So if you have a conjugated pi system, and you want to do a free radical halogenation, this can be done under two different types of circumstances. You can use the diatomic halogen, which is usually bromine but could be chlorine, or you can use the molecule NBS. I'm going to use NBS just so that we can see something different. But this could be initiated, as you've seen previously, with Br2 in UV light. If you use NBS, you typically would use an organic solvent and some UV light. So the first step would be the initiation. With NBS, what you're going to do is you're going to break the nitrogen-bromine bond in a homolytic fashion. Normally, we don't break bonds between two atoms that are, in a polar covalent bond. But this one is unique because one of the radicals that is produced has resonance stabilization of the radical. So we're going to be able to break this bond homolytically. And this will generate for us a bromide, or a bromine atom, not even a bromide, but a bromine atom. And it also generates for us this other radical, which has resonance stabilization through the conjugated pi system. So for a moment, I'm going to deviate from the mechanism and show you the resonance of the succinimide radical. This radical is part of a conjugated pi system with the 2 carbons and the 2 oxygens, since all of these atoms are sp2 hybridized. So if you want to show resonance, you could show this electron binding up with this one, the other electron going to the oxygen here. This is an option. And the radical would now show up on the oxygen. You could also show this radical binding up with the other carbon of the other carbonyl group to make a different resonance structure. And in the end you might say, those look the same, Sister Stoll. Well, that's kind of the point. They're supposed to look the same. They are chemically equivalent resonance structures, but they are different resonance structures since they're showing these at different oxygen atoms. But this does, as you can see, have resonance delocalization of the radical over 3 atoms. So it's a very stable radical. Now once the reaction has been initiated and you've produced this bromine radical, you can then use it to do some propagation. Now, this reaction is always a free radical addition of a halogen to an alkane. So you want to look at the 2 alkyl carbons, the alkane carbons, and think about if you can make a conjugated pi system by adding to either of those. If you added to the carbon I'm showing in blue here, right here, you would have a conjugated pi system through this part of the molecule, but it only have 2 resonance structures. If you added it here, you would have resonance through the entire conjugated pi system. So you want to use the one that would make the most stable radical. So I'm going to redraw that molecule here for us again so we can see it. And what we really are going to do is we are going to remove a hydrogen atom from this position down here. So bromine will come in, take a hydrogen atom, the other electron is given to the carbon. So we make HBr, and now we're going to have our allylic radical. And this one has a fairly long conjugated pi system, so I'm going to draw all of the resonance structures of this radical. So there are 3 resonance structures for this particular radical. Normally we would not choose to do a free radical halogenation under these types of circumstances because we would produce more than one product. So this would not be very productive chemistry in that sense. Once you have this radical, it can react with another NBS molecule. And I'm going to draw it off to the side here in kind of tiny letters. And I don't want to draw in all of the electrons and all of the atoms, so I'm not going to. But the point is, these radicals can react with the radicals you see here. It's another propagation step. So we could have the bromine add to this position. The electron goes back to the nitrogen. Or it could do this with the other 2 as well. As a result of this, you're going to end up with 3 products in this particular case. That one's not going to work, sorry. Didn't draw that right. Okay, these are the 3 products that we would form. And because it is a propagation step, you'd also make some more of the 6-amide radical that again has resonance through the conjugated pi system. And I'm not going to bother to show a termination step, but it would terminate. The point is, though, you make 3 different products. And so this isn't the most productive way to do something like this, but this is what's going to happen if you try doing a free radical halogenation with the conjugated pi system, where the radicals are not equivalent by resonance.